Question 5. A random variable is the consumption of a household's consumption of electricity measured in kilowatt hours. And we know that this random variable is normally distributed with a mean of 1,650 kilowatt hours and a standard deviation of 320. For part A, we want to find the probability that our random variable is less than 1950. So we want the probability that a random household will consume less than 1950 kilowatt hours of energy. I'm going to call our random variable x. Now, to calculate normal probabilities, we generally want to convert to z-scores so that we can easily calculate the probabilities using our z-table. So this is our formula for converting our x values to z-scores. So we're going to use this formula and convert 1950 to the corresponding z-score. So I'll take 1950 minus the mean of our random variable, which is 1650, and divide by the standard deviation, which we're given is 320. I can plug this into my calculator, and I get that 1950 minus 1650 over 320 is 0.94. So the probability that a household consumes less than 1950 kilowatt hours is equal to the area to the left of z equals 0.94. I can find that area, that probability, from my z-table. So I go down to 0.94, z equals 0.94, 0.94, that tells me that the area to the left is 0.8264. Therefore, the probability that a random household will consume less than 1950 kilowatt hours in a month is 0.8264, or about 82.6%. Part B. We want to find the percentage of households that consume between 900 and 1,300 kilowatt hours per month. In other words, what's the probability that our random variable is between 900 and 1,300? So I'm going to convert 900 and 1,300 to z-scores. 900 minus our mean, which is 1650, divided by our standard deviation. I'm going to convert 1,300 now. The probability. So I'm going to calculate this z-score, plug this into my calculator. I should get negative 2.34 for this z-score. For this z-score for 1,300, I should get negative 1.09. Remember, to find the probability that z is between two values, I'm going to draw it here. Using my z-table. My z-table, if I look up negative 1.09, it'll give me the area all the way to the left. I just want this shaded area, so I'm going to subtract out the area that I don't want, which is the area to the left of negative 2.34. So this is equal to the probability that z is less than negative 1.09, the area to the left of negative 1.09, and subtract the area to the left of negative 2.34, which we don't want. Okay, so now I'm going to read these probabilities off my table. So I look up negative 1.09. Let's see, negative 1.0 is here. 0.09 is here. So the area to the left is 0.1379. Next, I'll look up negative 2.34. Negative 2.3.04. So the area to the left of negative 2.34 is 0.0096. I can plug this into my calculator and I should get 0.1283. So the probability, or the percentage of households that consume between 900 and 1300 kilowatt hours is 0.1283, or about 12.8%. All right, part C. We want to know how much electricity are the top 10% of the population consuming monthly in the winter. So the top 10% of people, I can represent that using a Z little graph, a Z distribution. So top 10% means that they're in the highest 10% of people. So these are the people that consume above some amount of energy. So the amount of people that consume above some threshold is 0.1, or 10%. And so we want to figure out what this amount is. What's the threshold? What amount of energy do you have to consume above to be in the top 10% of consumers? So we know that the area to the right is 0.1. So that means that the area to the left, this area here, must be 0.9. So let's find the z-score corresponding to an area to the left of 0.9. Do I see 0.9 on this side? Nope, so I'm going to go to my positive values. Now we're getting close to 0.9. I want to get as close to 0.90 as I can, and that looks like this is the closest I'm going to get. So the z-score corresponding to approximately 0.90 is 1.28. I found the area to the left, closest to 0.9, and I'm reading off the corresponding z-score, which is 1.28. So I can replace this here with 1.28. So I know the z-score. Now I want to put that in terms of our variable kilowatt hours. So I want to convert from the z-score back to a random variable x. Now remember, this is our conversion formula. To make it easier to convert back to x, I can just rearrange these. So I'm going to multiply both sides by sigma and add mu to both sides, and I get that x is equal to the standard deviation times z plus our mean. So we're given the standard deviation and our mean, and I found the z-score, so I just have to convert. So I get that x is equal to 320, the standard deviation, times 1.28, plus our mean of 1650. And if I put that into my calculator, that's about 2059.6 kilowatt hours. So I know that to be in the top 10% of consumers of electricity in the winter, you need to consume at least 2059.6 kilowatt hours of energy. Part D. We're given that a randomly selected household consumed 2,000 kilowatt hours of energy, and we want to figure out, is this unusually high? One way we can do this is to use the empirical rule. Remember that the empirical rule says that 68% of our data, if we have a normal distribution, lies within one standard deviation of the mean. The empirical rule also says that 95% of the data approximately lies within 2 standard deviations of the mean. So, if our household consumption, in other words, if 2,000 kilowatt hours is within 1 to 2 standard deviations of the mean, then our household is not unusual. So let's see, 2,000 kilowatt hours. So our mean is 1650. And the standard deviation is 320 kilowatt hours. 1650 plus 2 standard deviations is 2,290. 1650 minus 2 standard deviations is, let's see, is 1,010 kilowatt hours. So if the household, if their consumption is in this interval within 2 standard deviations of the mean, so if it's within the interval then the household's not unusual. So let's take a look. Our household consumed 2,000 kilowatt hours of energy. 2,000 kilowatt hours is between 1,010 and 2,290. So 2,000 kilowatt hours is in the interval. So this household is not unusual. So this is one way you can use to determine if an observation is unusual. Figure out what's the interval that's 2 standard deviations from the mean. So calculate your mean minus 2 standard deviations and calculate your mean plus 2 standard deviations. If your observation is within that interval, if it's within 2 standard deviations of your mean, then that observation is not unusual. That's our first method. Another method we can use is figure out What percentile is our household, is our observation at? In other words, what percentage of households consume less than 2,000 kilowatt hours of energy? So I'll call this the empirical rule method, this first method, and I'll call this method the percentile method. So we want to find what percentile our observation is at. So figure out what percentage of observations lie below it. So the probability that x is 2,000, x is normally distributed, so we can convert this to a z-score. So we take 2,000 minus our mean, which is 1650, and divide by our standard deviation of 320. This is equal to, this z-score is 1.09. The probability that z is less than 1.09 is, let's find 1.0, 1.09. So the probability that z is less than 1.09 is 0.8621. So our observation, this household, I should say, is at the 86th percentile. 86th percentile is not super unusual. So we'll say this household does not consume an unusually high amount of energy. In general, if our observation is above the 95th percentile, we say they're unusual. '86th percentile is below the 95th percentile, so this household's not unusual. That's our second method. Our third method is, we see what's the probability of observing a household that consumes as much or more energy. So what's the probability of seeing an observation as or more extreme than this household? Kind of like the p-value. The probability that x is greater than or equal to 2,000. Well, x is normally distributed, so I convert this to a z-score. We did that in the last problem, so we want the probability that z is greater than 1.09. This is equal to 1 minus the probability that z is less than or equal to 1.09. I calculated that in my previous method. So I know that this is equal to 1 minus 0.8621, which is 0.1379. So approximately 13.8% of households consume more than this household. That's still a fairly large percentage. As long as it's greater than about 5%, we say that the household's not unusual. So this household is not unusual. The last thing to note is that these z-scores, so the z-score associated with consuming 2,000 kilowatt hours of energy, that z-score is 1.09. Well, what does a z-score represent, actually? What does 1.09 mean? Well, actually, 1.09 is, so because 2,000 is associated with the z-score of 1.09, that means 2,000 is 1.09 standard deviations away from the mean. So the z-score tells us exactly how many standard deviations away from the mean our observation is. So that provides some context to number 1. We can see that our observation is exactly 1.09 standard deviations away from the mean, which is less than 2 standard deviations. Remember that if a household is within 2 standard deviations of the average, they're not unusual.